All right, this is PowerPoint 2C, Molecules and Ions, and it's going to be a really good idea as I'm going through this particular lecture to have this PowerPoint out. There's going to be a lot of visuals that will be useful for you to refer to. I'll try to do some drawing on the board, but just make sure that you have that PowerPoint handy. In this chapter, we're going to try to distinguish between molecules and ions. So atoms, the atoms we've been talking about that you can sort of are represented on the periodic table, those things connect together to form stuff that we see. And when they connect together, they make larger units that are still really stinking small, but those larger units, we call them molecules, or we call them ions, and those molecules and those ions, generally speaking, are what build the stuff that we see and the stuff that we interact with. And so that's what this chapter is about, is sort of how we think about atoms connecting to make these larger things, and also how we name. How do you name, let's say, when two hydrogen atoms and one oxygen atom connect to form H2O, we call that water. But there's also sort of a systemic way that we name these molecules that are made from the combination of atoms. And we'll be learning about how to name some compounds in this chapter. So first, let's go to slide 2. We're going to define a molecule. I'm going to write this right here on the board. So a molecule. And you already have, I'm not going to write this. I'm going to just you have this sort of specific definition. I'm just going to kind of define it here the way I sort of think about it. A molecule is a packet. It's a tiny packet. We're talking things on the size of molecules and atoms here. It's a very tiny packet of matter made by atoms, I should say two or more atoms, connected. So let's just think of the simplest molecule that there is. It's actually hydrogen, and I'm going to draw two H's connected by a line. And this is symbolic of what we think is going on in what we call the hydrogen molecule. So you have these two separate hydrogen atoms, and we'll talk about this later in the course, but those two atoms, they combine, and they stick together chemically. And then those two atoms that have combined, they're stuck, and they sort of travel around together in a single packet that we call a molecule of hydrogen. And we abbreviate sometimes it by H2, and that tells me when I see that, this is referring to a molecule that's made of these two individual hydrogen atoms that stick together in a packet. It's like water. We know water is H2O, so we refer to water in this way. But if I actually think about the water molecule, it actually kind of looks like this, at least the way we think about it. A single oxygen atom connected to two hydrogen atoms. You'll also know I wrote a little bend here. And I write that there because we know that actually the angle, we actually know what the angle is between this hydrogen atom, this oxygen atom, and this hydrogen atom in water is 104.5 degrees. Isn't that remarkable that folks have figured that out? So these molecules, they're formed by the combination of atoms connecting together in a certain way. It travels together in a packet, so an H2O moves, the hydrogens and the oxygen, they move together as a single entity that we call a molecule. And they have certain shapes associated with them as well. And we can tell what these shapes are, remarkably enough. So if you go to PowerPoint slide number 3, you'll see some of the varied ways that we sort of symbolize molecules. And you'll see, for example, there's a molecule called propanol. And there's a different molecule called isopropanol. So I'll write the names up here. Propanol and isopropanol. And I can write the structural formulas for both of these. Excuse me, the molecular formula, C3H8O, C3H8O. They're identical in terms of their molecular formulas. They're not identical molecules, and we'll learn why in a bit. But what this tells us here is that in a molecule of propanol, there's going to be 3 carbon atoms, there's going to be 8 hydrogen atoms, and there's going to be a single oxygen atom. So if you see an element written with no subscript behind it, it's assumed to just be one of them. Isopropanol is the same here. Now we can also draw what is called the structural formula for these 2 particular molecules. And the structural formula gives you some indication, although not a perfect indication, but it gives you some indication of how the atoms are arranged in space. So propanol is going to look like this. There's going to be a carbon attached to 3 hydrogens, and then there's going to be attached to another carbon that's connected to 2 hydrogens, and then there's a 3rd carbon that's connected to 2 hydrogens, and then an oxygen, and then a hydrogen, like that. So this gives me an indication, this isn't perfect, but it does better than this, of how the propanol molecule is arranged, sort of the connections between the atoms and how those are arranged. The structural formula is going to allow us to see the difference between this molecule and this one. I hope you can see it. So here, I'll draw the structural formula for isopropanol. So far, everything's the same. Here's where it gets different. In this case, we kind of envision, we call this an OH group. In propanol, the OH group is going to be connected to one of the carbons on the end of the carbon-carbon-carbon line. In isopropanol, the OH group is connected to the middle carbon. And remarkably enough, that tiny little shift makes these 2 compounds different. They're similar, as you can probably imagine. I mean, they're very similar structurally. But these compounds, they have different melting points. They have different boiling points. They have different, slightly different ways that they react with various compounds. A lot of it's very similar. I mean, both of these burn. They both burn an oxygen to release energy. They're both liquids at room temperature, but there are differences that can be measured between these 2, both chemical difference and physical differences as well. Now, sometimes you'll see these structural formulas written in a condensed way that sort of conveys both the molecular formula and the structural formula in a sort of a combination of ways. And I'll show you this here. The way we do this is we're going to sort of view this as a CH3. And then this is going to be written as a CH2. And this is written as a CH2OH. So this would be the condensed formula for propanol. And similarly, if we were going to do this here, I'll draw it up above here because it's run out of room here. But this is going to, again, we've got our CH3. And then our middle, we'd call this a CHOH. And then a CH3 on the end. So notice, these structural formulas are able to distinguish between propanol and isopropanol, whereas the molecular formulas are not. I mean, they're both C3H8O for both propanol and isopropanol. If you'll if you'll move your PowerPoint to slide number 4, you'll see another way that we represent molecules. It's called the ball and stick model, and you'll often see this in your text, and I'll often be using these in lecture as well. And this shows the connectivity between the atoms in a way that tries to convey some of the three-dimensional arrangement between the atoms in the molecule. So if you look at the structural formula, everything's drawn with right angles. Well, that doesn't really convey the way things are. And you'll notice if we look here at the ball and stick forms of the two forms of propanol, as I'm looking at this, I see that, yeah, those connections between the carbon atoms, those aren't right angles. I see some angles there that are very different than that. And so this tries to give you some three-dimensional perspective, and the sticks are used to show the chemical connections between the atoms. I like this type of model when I'm thinking about molecules, but it's not the most, should I say, accurate. And if we go to slide 5, this gives you probably the best representation of the way the molecules are. They're models, so they're not perfect. But nevertheless, if you look at the space-filling models of these two forms of propanol, on the left you can see propanol, and on the right you can see isopropanol. These space-filling models give you some indication of how these atoms really look like, as best as we know, in real life. And try to remember that when we're talking about molecules, we can't ever really see these things. We just poke around and try to figure out what's going on as best as we can. And these space-filling models are a representation of what we think is going on. When you see the space-filling models, or you see the ball and stick models, you should recognize that carbon is always represented as a black sphere. The oxygens are always going to be listed as a red sphere, and the hydrogens are always going to be white spheres. Some others that you should probably be familiar with is nitrogen atoms are often listed as blue spheres, and sulfur, for example, those are going to be listed as yellow spheres, and that'll pretty much cover most things for you if you just keep those in mind. Okay, so that's the introduction to molecules. We're now going to talk about ions for a little bit. So there's two different types of compounds that can be made. Remember, compounds are things that are made from two or more elements. So let's just take this compound. First one is H2O. And then a second compound we're going to write as NaCl. And this first compound here, this is made of molecules. And a compound that's made of molecule is called a covalent compound. So because isopropanol and propanol are both made of molecules, those would both be considered covalent compounds. I'll just write it up here, C3H8O, made of molecules. There's another type of compound that can form, and these compounds are made out of ions. So we call them ionic compounds because they're made from ions. And that happens to be, one of them happens to be sodium chloride. That's just table salt. And I want you to look at the diagrams or the models on slide 6 of your PowerPoint. And you can see that the arrow pointing to the ionic compound, what you see there are some green spheres and some blue spheres. And those green spheres and those blue spheres, they're arranged in sort of like a lattice or an array. And as I look at that lattice or that array, I see a whole bunch of them. It's very ordered and very beautiful. But I don't see, say for example, an individual packet of sodium chloride. What I see are a bunch of sodium ions that are blue in color, and I see a bunch of chloride ions that are green in color, and those things connect together on and on in a very organized fashion over and over and over again to give us what we call an ionic lattice. So ionic compounds are not made of molecules. So it's not like there's a packet of NaCl that's stuck together and moves around or is stuck like this in the lattice. What happens is you have an enormous number of sodium ions, an enormous number of chloride ions that are stuck together in this large array that we call the ionic lattice or the entire ionic compound. We're going to contrast this with the other picture that you see on slide 6 of your PowerPoint, the covalent compounds, and what you see there is you see what looks like a jumble of that. That's a representation of water molecules. Those are ball and stick models of water molecules, and in that case you can pick out individual H2O molecules. So covalent compounds are substances that are going to be composed of molecules or otherwise neutral components.